I'm very pleased to welcome my former PhD student, Kuo-Chuan back to Illinois. Kuo-Chuan got his PhD in 2013, working with me and Ron Tam on type 1a supernovae and binary systems. I think one of the things we showed, for example, was that the symbiotic channel could not work for type 1as. Be too much hydrogen in the spectrum. And he went on to a postdoc with Friedel Thielemann at University of Basel in Switzerland, working on core collapse supernova simulations. And then from there, back to the United States with Sean Couch at Michigan State, also on type 2 supernovae, core collapse. And then in 2018, he returned to his home country, Taiwan, as a professor, assistant professor at National Tsinghua University in Hsinchu, Taiwan, which is where all of your CPUs for your smartphones are made. Anyway, so he's on his first sabbatical here in the US this year, and so we're very lucky to get him to come over and tell us about his current work on gravitational waves from super.
Okay. Thank you very much for the introduction. It's such an honor to have the opportunity to come back to my alma mater. And also, thanks, Paul. Yeah, it's very nice to see you again here and also see many old friends of Illinois. So it has been more than 10 years since I graduated. It's such a long time. But somehow yesterday, I tried to draw in between Champaign and Urbana. Somehow I do remember all these roads. I don't need GPS at all. And I managed to go to the restaurant and managed to walk into some parks and bring my kids to have fun in the playground. So that reminds me lots of memory in Champaign and Urbana. Okay, so this is more than 10 years ago. So you can see the autonomous department looks exactly the same. But people, people are getting senior. Yeah, and it was me, Charles, always here. Yeah. So and this was my my office when I first arrived in Illinois. I still miss this office a lot. Although it's crowded, but very comfortable, especially this chair. Yeah, I think I slept a lot on nights. Yeah. So it's such a wonderful memory, and I'm so happy to have this opportunity to come back. And this photo is actually taken on the date of my PhD defense, which I think was in May 2013. You can see the alma mater was quite old at that time, it's in the year. As Paul mentioned, my PhD thesis project were about binary system in type 1a supernova explosion. So we know that type 1 supernova explosion are explosion of white dwarfs. But at that time, one of my thesis committee members, Professor Ron Webbing, asked me a question. I still remember that he asked, what if the explosion is from Kuo-Chuan supernova? So what would be the difference? At that time, I think I didn't answer well. Fortunately, I still passed the exam. And also very interesting is I got a postdoc position in Switzerland and start to shifting focus to Kuo-Chuan supernova. So I hope today I can answer Ron's question better, and I hope you can also enjoy my talk. So feel free to interrupt me at any time to ask questions. Okay, back to the science.
Could you clear that?
Oh, and I see my mouse comes. Oh, no.
Okay, don't worry.
Okay, yeah. So this is an outline. First, I will give you a basic background introduction, why Kuo-Chuan supernova are important and why it's interesting, what we can learn from Kuo-Chuan supernova explosion. And I will also explain what is called the supernova problem, which spans several decades in theory to understand how to blow up a star. Actually, it's quite difficult and quite challenging. And also, there's engines that drive the explosion. The mainstream engine now is highly related to this so-called the neutrino-driven explosion, which involve lots of neutrino interaction with the matter. And how does light make star to explode? And also there are some other possibilities that can make the star to explode. For example, if you have a fast rotation, then the angular momentum transport can be more efficiency. Then you can drive rotational instability and all magnetic rotational instability that involve magnetic fields. So I will also cover about this kind of different engines on supernova explosions. And also most important thing is we know that the neutron star and stellar mass black hole are produced from co-collapse supernova. So how to form neutron star and how to form black hole, stellar mass black hole are also important, and especially for co-collapse supernova is a very ideal multi-messenger sources because it involves not only explosion in an EM wave, but also it will emit neutrino emissions and gravitational wave emissions. And whether we can detect the gravitational wave from co-collapse supernova is also a very important questions. And I hope our simulation can provide some hints to understand what the gravitational wave function look like and whether we can detect it or not. And finally, I will summarize and conclude. So I will start from this very beautiful image taken by the WST. So this is the case A supernova remnants. Case A is a very young supernova remnant which has about 350 years old, and it's a galactic supernova remnant. So it's located about 3.5 kiloparsec. So it's quite close. So with the WST, you can see the near infrared and mid infrared emissions. And you can see lots of details from these supernova remnants. So the first things you will notice is that the explosion is not spherically symmetry at all. So it has lots of detail, lots of substructure. But in the past, because for numerical efficiency, people try to draw a star from one dimensional first. But we can see the explosion is not symmetry at all. It's even not two dimensions. So it's indeed a three-dimensional problem. And also from these ZWST images, you can also see that the explosion, actually it has this red region showing the main shock actually is interacting with the constellar medians. And that creates some outflow here. And also there's like a black hole due to some high-speed jetta that penetrating the shell. And also very interesting, the newly discovered is this green region. People call it the green monster, which you can see that there are actually some holes of this constellar median interaction. And nowadays, some new simulations suggest that this could be some interaction of the shock-heated constellar median. And to have this size of this bubble, that require a certain of magnetic field to have this kind of structure. And also, newly discovered feature is this light echo signal. That also give us understanding to look these supernova remnants from different angle. Then we can understand the structure of supernova remnants better. And also,
before you go on, with the CSM holes, can you just say for a moment what you think those are? Are those bubbles around individual stars? Is it magnetic fields? What's the,
okay.
what's the idea?
So this is newly discovered, this one. So basically, because it need to be hot, so it's heated, so it's pretty hot. So there were some debate between whether this came from the ejecta or came from the constellar median. And I think it was this paper, no, this paper, and this is a observation paper from the X-ray, suggests that this is actually from the circumferential median. I forgot the exactly argument, but if that's correct, this paper does some three-dimensional simulation of the evolution of supernova remnants, and they include magnetic field. And by their simulation, they actually try different strengths of the magnetic strengths. Then they can find out the size and also the growth rate of this hole depends on the strength of the magnetic field. Yeah. Yeah. So. Okay. Yeah, and also from this other X-ray observation revealing the composition is also highly suggests that the explosion are asymmetry. You can see, like, for example, this iron is not like spherical symmetry. It's not only from the center, but from other different regions. So let's make us to question. So how to make these complicated features and how to make the explosion happen. So if we go back and look into even younger supernova remnants, but in LMC. So this is the famous supernova 1987A. This is maybe the close supernova remnants like exploded in modern digital astronomy area. And also at nighttime, we do see neutrino emission actually detected by neutrino detector. But at nighttime, only a few events were detected. But we know there must be some neutrino emitted from coconut supernova explosion. And also from the supernova 1887A, you can see there are some like stable ring structure happens. And also there are several knots happening there. So that also related to the circumstellar media interaction. And also even some people suggest that this maybe came from merger of binary systems. And also due to ZWST, so 2 years ago, they also trying, because at that time, people think, okay, there could be a neutron star forming from the supernova 1987A, but we haven't detected until 2024. So in this emission, I think it's from this argon emissions. This, although we cannot resolve it, so it's unresolved point source, but you need to have a neutron star in order to have the model for either neutron star cooling or pulsar winds to have this kind of emission. So this is evidence saying that there's indeed a neutron star formed in the center of supernova 1987A. Okay, so that's very interesting. So we know neutron star can form, neutrino will be emitted, but then how to go back even earlier, how to blow up the stars. So then let's go back to the supernova physics 101. From your general astronomy physics, you know that we have a supergiant and collapse to become a neutron star. So the gravitational release from the binding energy is about 10 to 53 Earths. That's a lot. And also from the observation of supernova, we can estimate how much mass is ejected, and also we can measure the velocity of the ejecta, and it gives you roughly the kinetic energy is about 10 to 51 Earths. So that means most of the energy is carried through other emission, which is the neutrino emission, and only 1% of the energy are released through kinetic energy. So the picture is like for the massive star, for the mass above about 8 solar mass, because gravity is so strong that you can have nuclear synthesis continues going until to the iron. So then you have this onion shell structure. And this iron core has a mass limit called the transit mass. Then once the iron core reaches these limits, then it will become stable and collapse from a few thousand kilometer to a proto-neutron star for about 100 kilometer. So because the neutron star is so dense, so neutrino can be trapped and are emitted through the electron capture, pair production, scattering, and so on. So it will emit lots of neutrino emissions, but the outer layer of the star still collapsing. So you have accretion keep powering these neutrino emissions. So to blow up the stars, you need to have so once the core reaches nuclear density, it will bounce and launch a shock wave. But this shock wave only carry a few amount of energy, and which might not be enough to power the explosion because some energy will be wasted to dissociate the iron. And also you have this accretion pressure to against the shock. So the idea is, what if this 99% of energy of neutrino can be reabsorbed into the shock, into the ejecta, then the 1% of energy might be enough to power the explosion. So this is the mainstream called neutrino-driven explosion. And this process, if we want to test from observation whether this process work or not, this actually cannot be done by EM observation because from EM observation we can only see the photosphere, right? But what I mentioned about this neutrino process, neutrino-driven explosion, happens in the region around the proto-neutron star, just the inner few hundred kilometers of the star. So, and the time scale can change a lot as well. So, for example, you have a core collapse from a neutron star. It takes maybe less than a second to get core bounce. And after core bounce, you launch a shock wave. But because of the accretions, the shock will stall for maybe a few hundred milliseconds. And then because of the neutrino heating, so there are a few scenarios which you can have shock revival. Because of neutrino heating, then you increase some heating efficiency, then you can make star to explode. Another possibility is if the neutrino is not efficient enough, then shock is not revived, then you have a black hole formation. So this could be a scenario called the failed supernova explosion. That means you can form a black hole, but without seeing a supernova explosion. And for the successful exploding case, because the explosion is asymmetry, so you can have ejecta going to outward, but at the same time, you also can have accretion together at the same time. So the neutron star mass will keep growing, and if it reaches to the maximum mass of a neutron star, then that neutron star will collapse again and forming a black hole. So then you can have a delayed black hole formation, and together with explosion, or in failed supernovae as well. And what I mentioned so far are the shock are still expanding and growing within the photosphere, and it takes hours to days to reach to the photosphere. Then you can have the shock breakout at night time. So in terms of multi-messenger physics, then for EM wave, we can see the progenitors of co-collapse supernova because we know they are super giant. So that means we can observe the EM wave, and we also do see shock breakout and later on explosion. But for the inner physics, what happened in these regions requires neutrino and gravitational wave emissions in order to test the physics of co-collapse supernova. So observationally, we actually do see the supernova progenitor. So we can see there's a red supergiant here. And after supernova explosion, then that star disappear. Then we think that's the progenitor of this co-collapse supernova. And also, we see the neutrino emission from co-collapse supernova of 1987A. So if we have another nearby co-collapse supernova, nowadays, now we have much better neutrino detector now. So then we can give even more constraints on the neutrino physics inside supernova. And also there's another case called the candidate of the failed supernova, which you see there's a star is appeared, but without seeing a supernova explosion. So this is evidence saying this is a failed supernova explosion. And of course, shock breakout. So for example, this is you need to identify this very early light curve. Although it's very difficult because you don't know where and when the star will explode. So you need to be very lucky, or you need to have very, for example, like LST might give some better chance to identify this shock breakout, but it is difficult. And you can see the shock breakout physics could be also very interesting as well. But so far, the missing point is we haven't seen the gravitational wave emission from co-pilot supernovae, and we are expecting to see it if they are close by. So one of my main research focus is now whether we can provide a waveform templates of co-pilot supernova in order for the future searches of gravitational wave from co-pilot supernova. Okay. So in the past maybe 6 decades, people studied a lot on co-pilot supernova physics. We know it can form neutron star and black hole, right? So general relativity is quite important. And also we know like neutrino is important, we should involve neutrino. Then people try to build the most sophisticated solver that solve all the necessary ingredients of co-pilot supernova, solving the post-event transfer equation, about these things, but doing this supernova simulation in 1D. So here is a movie. You can see the density, entropy, and this is an electron fraction and the velocity of this 1D supernova explosion. So you see the electron fraction is lower than 0.5. That means it's neutron rich. So you are forming a neutron star. And you can see this simulation. You can see the neutron star getting high mass, will form proto-neutron star, launch a shock wave, shock stalled in about 150 kilometers. And you have the neutron star here, but the velocity, so you have positive velocity here, radial velocity here, but shock stall. Then this is a failed supernova cases. So it's actually making the progress of supernova become very slow because it's difficult to get the explosion. But now, because we have much better supercomputer now, we can do multi-D, we can do 2D and 3D. And then the thing is that if you have multi-D, then we have much better chance to get supernova explosion. It's because in 1D you are only allowed to have radial motions. And in this picture, you have a proto-neutron star. It's a very hot. Then you will emit neutrino. So if the neutrino are emitted, so it will cool the neutron star a little bit. And there's another layer which the emitting neutrino can be reabsorbed. So you have this heating area, or we call the GAN region around here. So in 1D, the matter are allowed only in this direction, and you are stay in this GAN region for a very short time. But in multi-D, because of the convections and turbulence, now matter can stay longer in the GAN region, for example, in this region due to convection. Then the heating efficiency can be dramatically improved in multi-D. And also there are some fluid instability, which you can see the motion is not symmetry. Then we can get explosion. So that means we need lots of physics, and also we need to do multi-D supernova simulation. So if you just summarize all the gradient you need first, of course, hydrodynamics. But sometimes hydrodynamics is not enough because we know neutron star can has magnetic fields, and we saw pulsars as well. And also, co-pilot supernova are related to the long gamma ray bursts. Sometimes we know there are magnetars. So we probably also need NHD as well. So that makes things complicated. And also, if we need neutron star and gravitational and a GR and for black hole formation and gravitational wave prediction, then we also need to solve general relativity, which is also a very painful and time-consuming solver. And of course, to have a neutron star, then you need a nuclear matter, and also for neutrino transport, you need to solve the Postman transport equation, which is a 7-dimensional problem because you have 3 dimensional in space, 2 additional dimension in the scattering angle, 1 dimension in the energy, and also neutrino has 6 flavors, right? So that makes things very complicated. So we need to have some approximative scheme. We cannot solve the Postman transport directly in 3D. So even with the current best supercomputer, it's still very challenging.
Is the GR done in full 3 space dimensions or just 1?
So there are different ways to treat this GR. So some people do full GR in 3D. In my code, we use this called effective GR way. So this is kind of post-Newtonian. So the correction is done in multiple terms, but we still have multiple terms from the post-Newtonian potential. Yeah. And also, so basically involve all 4 fundamental forces: gravity, EM force, big force, strong force. And also there are additional complexity due to multi-D effect, due to stellar rotation, turbulence, and fluid instability, blah, blah, blah. And also we need to cover a wide range of density and temperature by including the stellar envelope and also the neutron stars together. So that makes everything very complicated.
Is it necessary to go from 2D to 3D?
Yes, it needs because in 2D, first thing is the turbulent cascades in 2D is incorrect. And the second is in 2D, you have this preferred axis, which will artificially enhance this fluid instability in this axis. So then sometimes you might overestimate the explosion in 2D. But 2D is still not completely useless. It still gives, because you can run more simulation in 2D, right? So it still be helpful in some sense. Okay, then for the supernova engines, as I mentioned, the mainstream engine is called this neutrino-driven explosion, which if some of the neutrino be reabsorbed in a matter, then you can power this explosion. And also, rotational instability can help. I will talk about it later. And also magneto-rotational explosion are possible. So let's start from the simplest neutrino-driven explosion. What I will show is one of our 3D simulation, which in this image you can see there's a blue thin layer. This represents the shock wave about 500 milliseconds after explosion, after 4 bounds. And then the back side is about 1,000 kilometers in width. And there's a neutron star hidden here. You can see the purple region. There's a neutron star here. And this orange color represents the entropy of the shocked material. That can describe the convection and turbulence happened around a neutron star. Okay, so let's start from 2 movies, which I will show. So the initial conditions are different. On the left is the 12 solar mass progenitor, and on the right is a 20 solar mass progenitor. And here we are showing the entropy slices on the XY planes. So there's no rotations and no magnetic field at this moment, just purely hydrodynamics with neutrino transport. So you can see for both cases start similarly. So you have bound shock wave and shock stalls in around between 150 to 200 kilometers. And you can see lots of convection happen. And neutron star is around in this region. So because of different compactness of this progenitor, so the accretion rate will be very different in these two cases. So for the 12 solar mass case, you have less accretion because this progenitor is less compact. So it looks more spherical symmetry. And at the end, you can see the shock still stalled, so you don't get explosion. So this is a case of failed supernova. On the other hand, for the 20 solar mass progenitor, because of the mass accretion rate is much stronger, then you are easier to develop this asymmetry behavior, which you could see now you get a supernova explosion, and you can have this high entropy ejecta in a certain direction, but you have the low entropy accretion into different regions. Then I can keep powering this neutron star accretion, and you can see the ejecta keep jetting in a certain field direction. So it's although they share same physics we use, but different initial condition can lead to very different outcome. And also from this successful exploding case, you can also see that the explosion is very asymmetry. So 3-dimension is still necessary. And this is only happened about 700 milliseconds, so less than a second at the core bounds. And the spark width is about 4,000 kilometer now. Okay, so to get even better understanding about this supernova simulation, I will show you another movie which I quite like it. It's a 3D rendering of the 20 solar mass progenitor case. So in this case, we will get a supernova explosion. So you can see again the same thing, the shock front is around this region. Then you can have last convection. Here is also still showing the entropy distribution, but you can see now the asymmetry is growing in time, and also the neutron star is hidden in this region. Yeah. Okay, so you can also see now we will take a little bit. The back size is about like 1,000 kilometers now, and we will carry a ball. And there's a fluid instability called standing accretion shock instability, or we call it SASI. That can be naturally driven this ejecta with some sloshing motions. And now you can see we zoom out to a backside about I think 3,000 kilometers in radius now. Then we keep it exploding. Okay, so very important fluid instability in corporate supernova is this called standing accretion shock instability, which means when you have a bounce shock going to radially outwards, but you still have accretion on the surface, then it's called a static shock. Although initially it's spherical symmetry, but it can naturally develop to fluid instability, and you can have this spiral motion of the SASI. And this actually can be reproduced by this water experiment. You can see you can form this spiral shock happens when you have this standing accretion shock. So this is very important.
Look at your previous movie. I didn't really see this spiral structure, and I was wondering, how do you know that it's the SASI and not, say, Rayleigh-Taylor instability?
Okay, yeah. So there are some semi-analytical analysis about how this SASI instability can be growth in time. So to make sure this is indeed SASI, what we do is we can measure how this shock evolve and compute this semi-analytical frequency of SASI and compare with the gravitational prediction we simulated. And if we match, then we have much better confidence in, okay, indeed due to SASI, but not other fluid instability. Yeah. And of course, in this case, you need to have longer delay time in order to make the SASI more growing stronger in this case. But in the previous movie, the explosion time is not that delayed, so it is less obvious. So the SASI is not very strong in the previous case, but is stronger in this example.
And what makes one or the other?
Uh-huh.
Why would SASE be more important in this particular?
Okay, so it's important because in several aspects. First, this is one way to amplify the asymmetry of explosion. Yeah. So if you have this large motion, for example, if strikes preferring to this direction, then you have stronger accretion in that direction, and this is in instability. Once it grows, then asymmetry will be amplified a lot. So that's one aspect. And the other aspect is this slashing motion carries an angular momentum. So, but the total angular momentum should conserve, right? So that means the neutron star inside will carry offset angular momentum. So that means you can spin out the neutron star without giving initial angular momentum. Yeah. Okay, question. Okay, no. Okay.
There's a question online from Brian Fields.
Oh.
Would you ask him to unmute?
You just say,
Yeah,
just speak.
just-
Yeah, I'm unmuted. Can you hear me?
Yeah.
Yeah. So Kuo-Chuan, on your the simulation in the previous slide, at the initial step, it looks like there are these convective cells, and there's a small there, and they look quite symmetric, and then of course they get randomized. Those initial cells, are those like a reflection of are they an artifact of the grid, or are those real?
It's grid effect plus real, because there's a so-called early Planck convection that's real. But in this case, is the Planck convection is amplified due to the grid effect. So I would say, yeah, partially real, partially artifact.
Got it. Thanks.
Can you describe what's going on in that water image, the water movie? Yeah,
Yeah.
what is actually happening there?
Okay, so here you have a water fountain, which you have a water inflow to mimic this accretion. So you have water going to this direction, and in here you have a sink which you inject water spherical symmetry in radially, and so you also have this standing shot which are accretion and water against each other. And then initially it's spherical symmetry, but later on you can develop this spiral shock happens. Yeah. So actually, I think this is also demoed in one of the museums in Europe to show this fluid instability, and this instability actually is discovered by supernova simulation. That's quite interesting. Any other question? Yeah. Okay. So as I showed, even without rotations, without magnetic field, if you have this neutrino transport and turbulence, then you can have supernova explosion. But we know rotation is natural, because from stellar evolution and also from binary stellar evolution, we know maybe half our star are from binary. So it's naturally to imagine the star to be rotating. Then the next question is whether this rotation will provide some special features in terms of dynamics or multi-messenger signal. So if you include rotations, of course, also depending on how fast the rotation. But so far we found that if the initial rotation rate is fast enough, then you can have this called low T over W instability. That can also drive this into one spiral instability. Here is again the entropy slice, and also this is a pressure gradient magnitude. You can clearly see this spiral feature. And also in the right is a movie showing this spiral instability with different resolution, numerical resolution. So here, if you have a cell size 2 kilometer and also a cell size with 0.25 kilometer, then you can see this numerical viscosity actually can suppress the turbulence pressure, then makes the dynamics very different. Okay. And also for the magnetic fields, so because we know cochlear supernovae are related to the long gamma ray bursts, then whether we can also produce this kind of long gamma ray burst events, or hypernovae, or this magnetar engines from this self-consistent supernova simulation. So there are many different groups trying doing HD supernova simulation now, and you can see the different groups have very different morphology. For example, if you have this spherical shell-like explosion, or you can have this monopole jets, like you have jet only in one direction, or bipolar jet features. So then that makes us some questions saying, so why and how to get this different feature if you are using the same progenitor, the same equation state, but maybe playing around the magnetic field strength and the rotational rates, because all these different papers, they are using different progenitor, different equation state, different strength. So it's very difficult to compare. So we go back to 2D because in 2D now we can run very high resolution 2D simulation and also run a lot of 2D simulation with a small cluster on the workstation. We can do that. In here we use the 40 solar mass progenitor and we try varying the initial magnetic field strength, seed strength, and also changing the rotational rate from non-rotating to slow rotating and fast rotating. And we do find there are some very interesting behavior. We can reproduce this bipolar jet structure and also other morphology depending on how you configure this magnetic field initial seed and also rotational rate. And very interesting things is if you want to get an R process nuclear synthesis, although now people believe it's R process mainly came from neutron star mergers, but in certain magnetized fast rotating scenario, you are still possible to have some R process nuclear synthesis yields. So this is the morphology category we discovered using the same progenitor model, same equation of state, but just different magnetic field and also rotation rate. So you could see the first case is again the failed exploding failed supernovae because we are using the 40 solar mass progenitor, which is a very, very compact progenitor. Without magnetic field and without rotation, it should become a black hole case. And depending on the rotational rate, the magnetic field strength, sometimes you can also get this monopolar jets or the bipolar jets. But very interesting is in certain region you can have fast rotation, but you don't get jet, but get this it's like butterfly or brain structure explosion, which very similar to the previous non-magnetized supernova results. But because of magnetic fields, so you can see the structure is quite different with the non-NHD simulations. So how to get these 4 different categories? Then this is the parameter space we discover depending on initial rotational rates on the x-axis, and this is the initial magnetic field seed strength. So you can see if there's no rotation, then if you increase magnetic field, you can turn from a black hole formation case to successful explosion if you don't have rotation. And then of course, if you don't have rotation, so you don't have jets in this region. So that kind of makes sense. But another interesting thing is if you don't have magnetic field, but only have rotation, it still fail to explode. This is maybe due to these 2D simulations, because when in 2D, when you have a rotation, you don't have the spiral mode in 2D, but the rotation can suppress the convection around the neutron star. So you also get failed supernovae and black hole formation for that region. And of course, if you have fast rotation and strong magnetic field, then you get this bipolar jet structure, which in these red colors. But in between, this region is much more complicated, and it's turn out it's not linear. So you have some nonlinear structure happening, which we believe related to the Stasi motion. So you can have either monopolar jet, because when you have Stasi, then you have a preferred direction. Then you can have monopolar explosion or bipolar jet explosion. And also on the right is showing the explosion time. So how fast the explosion can happen. For the bipolar jet cases, it's usually happen in a very short time, 100 milliseconds, or less than 200 millisecond explosion for the bipolar jet. And for the monopolar jet region, you have more delayed explosion in these complicated nonlinear regions. And for the neutrino-driven explosion, it's also then highly depends on the rotational rates for this region. Okay, so these are okay.
So,
X left and graph.
This is the initial
Like there's an X in a
Oh,
box.
this is the case which it crashed earlier, and we cannot distinguish the morphology at that time.
so the morphology you showed in the previous slide, they look very different,
Yes.
but they're still very much focused on the thousands of kilometer sized box. If we look at the supernova remnants, would those morphology signatures be completely washed out if we look at several parsec scripts from observations?
Yeah. So here so far, that's a good question. The scale I showed are just few thousand kilometers still within the photosphere, and when it propagate, I think for example, in this case, the neutron star will be still offset, so it won't be perfectly at the center. I think that's still true. But for example, whether you can keep this jet morphology, I think that's maybe very difficult. It may be washed out later, especially after shock breakout, which we are not able to run that long with our current code. But that's an interesting topic. Some people actually try to continue this simulation in a much bigger box, cut the neutron star, and try to evolve to supernova remnants. So that's a very interesting topics to study.
But so far, it's hopeless to use a supernova remnant morphology to tell what kind of mechanism at the sense engine.
I think there are some hints, but not exactly, not one-to-one link. Okay, so then this parameter study was done in 2D, and of course the nature is 3D. So then we also try to do this HD simulation in 3D, but because our supernova computer in Taiwan is quite expensive to burn the CPU out, so we actually I collaborated with a lot of colleagues in National Taiwan University. He has another GPU code called Gamer. Then we port another simplified version. So this is the neutrino transport is much simpler than the previous one I showed, but we can do high resolution HD simulation in 3D with Gamma. I think this is only done by about 8 GPU cards. It's a gaming card, so it's much less expensive than using supercomputer, and that can be done by some homemade cluster. The most important difference is in 3D that you can have this spiral mode. That will make the morphology could be very different with what I show in 2D. And also, this the magneto-rotational instability will be happen in supernova condition as well. And here I show the magnetic energy density from another supernova simulation. and you can see magnetic field is quite high. I actually could be developed in the proton neutron star, and also even possible in the shocked GAN region. Okay, so again, then we try to do similar parameter study in 3D again, so here different color represent different initial magnetic field strengths, and different line style represent different resolution. And different. So these are, we actually tried two different rotational rate, but here I show the same rotational rates. So we are not changing the rotation, but only changing the magnetic field. So you can see the NRI can grow quite fast, no matter which the initial field strength you have. Then you can keep raising this average magnetic energy inside the proton neutron star. You can see you can quickly reach to. Okay. Oh, yeah. So then it quickly enhance to a certain threshold. But later on, no matter which initial field strength you have, then will keep similar. But if you do the same things in the heating region, GAN region, then initial magnetic field strength in the GAN region that's outside the neutron star, but have very strong neutrino heating, then it does have very different dependence on the initial magnetic field strength. And also the ratio between magnetic energy and the turbulence energy could be interesting as well. Okay, so that also means we need if we do magnetic field and doing in 3D, then all the dynamics can be highly sensitive with the configuration. But the question is whether this configuration change the overall outcomes or not. Okay, I think I need to speed up a little bit. Okay, so to get gravitational wave, of course, gravitational wave came from the perturbation of the density, right? And in binary mergers cases, you have two black hole mass or two neutron stars which orbiting each other. But in supernova, basically you only have a single neutron star. And we know there's no monopole or even dipole gravitational wave emission. So to get gravitational wave from Kuo-Chuan supernovae, you need quadrupole perturbation of this neutron star, and that require this neutron star convection, which you can show. This is the velocity magnitude, and also the velocity magnitude on the neutron star sphere surrounded by the fluid streamlines. Then you can see actually the surface of the neutron star actually is very turbulent, and there are lots of convection. And also, as I mentioned, the Sashi will actually induce the rotation of the proton neutron star. Okay, so this is the another example showing how Sashi spin out the neutron star. So initially, it's a non-rotating case, but the gray dots showing the angular momentum direction, and the color dots are the Sashi direction. So you can see that at the early time, so these are the time. At early time, they are kind of randomly distributed because there's no rotation at the beginning. But at the end of the simulation, you can see there are two box region and anti-correlated. So that means the Sashi carries the angular momentum in one direction, and the angular momentum is going to the other direction. Okay. And the black hole can also form in, as the two channel I mentioned, you can have either failed supernova explosion or delayed black hole formation. So in here, we use 40 solar mass projection again. So without rotation, that's the green line, then you get a failed explosion. This is density. You can see there's a second collapse. About several hundred milliseconds later, you can form the black hole. And one very interesting thing is this blue line, which you have slow, slightly rotation. Then you can have an explosion. So this is a shock radius evolution. You have explosion because shock radius expanding. but black hole formation at the same time. So that's also quite interesting. Okay, then maybe I just skip this part. Of course, the equation of state of the neutron star also matter as well. So we test with different equation of state on how black hole formation will be delayed due to different equation of state. So that means if the black hole formation time is delayed, then that means you can have more time to emit neutrinos in gravitational wave. So that will make the total neutrino emission be much longer if you have more delayed black hole formation. Okay. Okay. And also, as mentioned, if we run the simulation longer, and then with different progenitor, you can see the morphology could be very different, and it's very asymmetry. So one of the ongoing project, which are during my sabbatical, is whether we can use this simulation data and to construct a tracer of the fluid trajectory and do nuclear synthesis to see if we can use this supernova data to estimate what the nuclear synthesis should look like. This is an example of our late time morphology. The red is the high electron fraction component. Blue is the low electron fraction component. You can see it's kind of anti-correlated and different composition should lead to different nuclear synthesis, which is very similar to this case A cases. Okay, and because we are doing neutrino transport, then of course we can also estimate the neutrino emission. And if we give some neutrino detector properties, then of course we can also estimate how many neutrino rays it should look like. I will maybe just skip this part. And the most interesting is maybe in the way. So this is my son, and I think it's about 1 year old, so which is maybe 7 years ago. We know in gravitational wave we can have two different polarizations, and whether we can detect this and also detect this gravitational wave signal is quite interesting. So you probably have heard about gravitational emission from mergers. You can see you have this initial in spiral phase, and also a merger signal, and then a ring down signal. So that's quite simple because it's just 2 point mass. But in quark-like supernova, you can see it's quite different. So you have this bounce signal, but this bounce signal is highly depending on the initial rotational rate because the rotation the centrifugal force will make the proton neutron star be formed. Then you can have this bounce amplitude will be highly sensitive to the initial rotation, and that could be a sign to estimate what's the angular momentum of the core. But later on, this signal could be very complicated. This is a spectrogram which will have gravitational frequency in Y and time in X, and different progenitor. You can see they have they share some similarity structure, but could be also very different as well. The similar structure is that all have this bounce signal. And also you have this red line represent the neutron star surface oscillation. So it can grow from 100 Hertz to kilohertz. And this white line is the Stasi frequency I mentioned. So this is the 20 solar mass pit, which you don't see much Stasi, right? So because you have this early explosion. But for the 12 solar mass part, actually you can also see the Stasi signal at very late time for this failed explosion. And of course, okay, I have this sum. Okay, so you can see this is the gravitational sum of this emission. You can see it's also very different with merger. So you have this bounce ball and then high frequency component. Okay, and then again, the morphology for this energy simulation could also be different. For example, if you have the bipolar jet, once the bipolar jet launch, you can have this very loud, low frequency component, and also for the neutrino-driven cases. But the peak frequency is similar because they have the similar neutron star with the same nuclear equation state. Okay, and then if you take a look about whether we can detect this, and then this is the SD or the characteristic strength in terms of frequency, you can see that no matter it's different progenitor model, whether it has rotation or not, whether it's magnetized or not. One important thing is if this is galactic supernova, so this is assuming a 10 kiloparsec distance, we have very high chance to detect this signal if they are from galactic supernova. But if they are extragalactic, then only this very fast and compact rotating case has much stronger strength, sensitivity, and then only very extreme cases you have better chance to detect it in extragalactic supernovae. But if you have this cosmic explorer on Einstein telescope, then we can also push the limit much better. Okay, I think I'm kind of run out of time, so I will stop here, and here is the summary, and thank you very much for your attention.
Yeah, so you are mentioning that your simulation can have some asymmetry. Is it possible that it can introduce some sort of a kick that we see in Gaia? There are some runaway star, which are thought to be that has been disrupted when two binary, one of the supernovae happened.
Yeah, you mean the neutron star kick, right?
Yeah.
Yeah, so actually, yeah, it's kids. Actually, we do observe that kids, but honestly, I don't have very strong confidence to comment on the number of the kick, because once the star exploded, honestly, it's difficult to keep the angular momentum conservation a little bit. So I would say the kick sometimes could be artificially amplified by the neutral stability issue, but we do observe kick. And also there are some people estimate this kick based on how angular momentum unconserved. Yeah, but there is there, and it should be partially physical and partially numerical.
Brian has a question online.
Yeah, I guess related to the neutron star, the kicks. You had one model that had a monojet, so only the jet in one direction, basically. Could you say a bit about what makes that happen, and do you get a stronger kick in that case?
Okay, so for this monopolar jet case, this is usually more delayed explosion, and we believe this is related to the SASI activity, because when you have SASI, then this slashing motion can move the ejecta in one special direction, and if you are lucky, then ejecta is preferring to, for example, to this direction, and then somehow you trigger the explosion. Then neutrino heating will just keep pushing the ejecta going to this direction. Then you can have this very asymmetry one jet explosion.
And does it give a strong kick?
It should give, but in 2D case here, it still conserves quite well, so we don't see much kick in this case.
Really?
You have much stronger appreciation in this direction.
Cool, thanks.
Which microphysics library did you use for the neutrino transport? And second, what kind of neutrino transport did you use here? Was it like an approximate scheme, or was it like the full Boltzmann that you talked about?
The first question is the neutrino library. Yeah, this is a standard Bruren race from Bruren 1985. And what was the second question?
Which neutrino transport? I mean, are you solving the full Boltzmann equation?
It is called isotropic diffusion source approximation. So it's approximated spin. So it's better than plasmic diffusion, but less than M1 transport.
Thank you.
Thanks for the great talk. Sorry if I missed this. It looks like you'll also get a gravitational wave signal from failed supernovae. What are the prospects of observing that with LIGO?
Yeah, for the failed supernovae case, so although you don't see EM wave emission, but you should still see neutrino and gravitational wave, and this is so this is okay. Yeah, so this is the green one is the failed supernovae case. And also for the failed supernovae, this is also the green line here. So you have much shifting high frequency because neutrons further cool, so you have much compact neutron star. So then emission will shift it to higher frequency for failed supernova cases.
Well, I'll ask the last question. So, so both the SASI and the low T over W instability produce M=1 perturbations. And how could you distinguish them, or is one always dominant over the other?
If you have low T over W instability, then usually it's explored quite early, so you don't have much chance to develop SASI. So the frequency will be different, but the low T over W frequency will be slightly higher than the SASI.
So you would see that in the gravitational wave spectrogram.
Yeah. And also it's usually louder than the SASI.
I see. Well, let's send your speaker. So